to open the 2022 Women in Engineering 25th anniversary. I am Cinzia Davia, I am the chair of the 25th anniversary Women in Engineering celebrations. So today we are opening the Extraordinary Women, Extraordinary Science Seminar Series. Throughout the year, we are going through this seminar series to celebrate science, and in particular the science which is being performed by outstanding and really extraordinary women within societies and councils. So societies and councils have been proposing champions, and of course those women, they have been really pioneering and performing outstanding science. So we will listen to them throughout the year. And as you can see, we are going to listen to those seminars with a frequency of about twice per month. So every 2 weeks on Fridays at 9 o'clock. We will also have other celebrations. And one of the closest one that I would like to bring to your attention is the 8th of March marathon, 12 hours to meet IEEE WIE from all over the world. So throughout this marathon, there will be really an opportunity to listen to women in all the regions, what they are doing, and the extraordinary things they are really performing. It will be an occasion to meet each other and get in contact with one another. So this event has been thought to celebrate networking and diversity. Don't forget to propose your men, or extraordinary men as we call them, men who have been helping women in their career. We know how this is important, and for this important milestone, we would like to celebrate men as well. So we have a nomination deadline, again, the 8th of March, 2022, and we will let you know how we will celebrate them at the end. So please look at all these events and how to nominate your champions on the website that you see here on the screen. And I will now pass the floor to Jen for some remarks for the WA chair. Jen, the floor is yours.
Thank you, Cinzia. And first of all, thank you very much, everybody, for joining today and for start the celebration of this 2022 with fantastic events, as Cinzia just mentioned. We are glad to be celebrating is 25 years of being this global network of IEEE members and volunteers that are dedicated to promote women in different areas in technology and to inspire girls around the world. Those are 25 years of pursuing our mission, our goals to facilitate the recruitment and the retention of women in technical disciplines globally. We have always envisioned this vibrant community focused on these women and men working together collectively to use our talents and make the difference in the benefit of humanity. And it is so good to see that vibrant community keep growing and keep making that aim, achieving that aim. I want to take a minute to thank very much Cinzia and her team for the fantastic program that they have for the year. I always joke with her. She promised us a celebration and she delivered way beyond our expectations with her team. And today I would like to also take the moment to thank Boshena for supporting us during this event. And of course, Dalma. Dalma is for many of us one of those examples in IEEE. She's leading the diversity and inclusion committee in the technical activities board beside her director position in the board of directors. So I thank you very much for joining us today, and I'm sure the committee is with me with that message. Nothing else to share today. The floor is yours, Boshena, and thank you very much, everybody.
Thank you very much, Cinzia, and thank you very much, Jen. for introduction. And this is just my great pleasure and honor to introduce Dr. Dalma Novak, and who has multiple functions, as you already heard. But for me, as I am almost 50 years in academia, is fascinating path that we will learn today, and especially young people. You can just see opportunities. I expect that we will learn about that moving from academia to industry. Dalma Novak is Vice President of Engineering of Octane Wireless, where she develops high-performance RF over fiber technologies for commercial, but also for defense wireless applications. She is at the same time honorary professional fellow in the Department of Electronic Engineering at University of Melbourne, Australia. This is gorgeous, great university, which I had the opportunity to visit several times, and she left that university. So I am curious what attracted her. And Dalma has over 30 years of experience working in the optical and wireless communication fields, and is internationally recognized for her work in microwave photonics and fiber radio technologies. For all these achievements, but she contributed to several book chapters. She has over 300 publications and patents. For all of this, she was selected to be IEEE Fellow in 2007. And in 2018, she received the IEEE Photonics Society Engineering Achievements Awards. And before, as I said, before her position, and she was co-founder of this company, before she spent 12 years as professor and and then she will tell us all about her path. She bachelor and doctor of philosophy from the University of Queensland, and amazing all the ways, as Jan already mentioned, to IEEE. Being a member of the highest board body of the IEEE Board of Directors is a really, truly recognition, but not only, is a trust. So she's director of IEEE Division 10, and she is, as Jan mentioned already, she is the chair of that very important, not only for IEEE, but for every organization, for every unit, for every institution. She is chair of Diversity and Inclusion Committee. The rest we will learn from Dalma. So Dalma, the floor is yours, and I cannot wait to hear about your fascinating path. Thank you.
Thank you so much, Boshana. Thank you also, Cinzia and Jen, for your very nice introduction. Let me just share my slides. And can everyone see my slides?
Yes.
Thank you. So I'm going to talk about my engineering career evolution. And as Boshana said, that she's very interested to hear how it was that I went from academia to industry. So I called this presentation Seeing the Light, given that my background is in photonics. And also some of that reflects part of my decision-making process with respect to making that transition from university to industry. So before I start, I just wanted to say how honored I am to be part of this Extraordinary Women in Engineering series in celebration of IEEE Women in Engineering and their 25 years. And I wanted to congratulate women in engineering for all of the tremendous work that the community has done and all of the volunteers over the years to promote gender diversity in STEM and really work so hard to recruit and retain women in the field. And the work is so important. And when I was president of the Photonics Society, I initiated our own Women in Photonics program, and I'm very proud of how that has evolved and the great success that it has had. So thank you. So I wanted to start off talking about how I started out. So I did my, as you, Bashena said, my bachelor and PhD at the University of Queensland. So I was 3 when my family emigrated to Australia from Hungary. I was born in Hungary. And after arriving in Australia, we moved to Brisbane, and that's where I did my education. So I always loved maths and science when I was in high school. So engineering was something that I really wanted to do. And when I started to read about engineering, because that was pre the internet, I learned that electrical engineering really matched my interests in terms of the physics aspect more than any other field. And so that's what I decided to go into. And doing my bachelor, I specialized in what was then an emerging field of communications, fiber optics. But I also had a background in microwave engineering and electromagnetics. And, you know, when I look back on my history and how my career has evolved, it's very interesting to see how those fundamentals of fiber optics and photonics and microwaves has really underpinned my technical work over the years and has really had such an impact in how my career has evolved as well. And that's right from the very beginning as an undergraduate student. So straight after I did my bachelor, I was offered a number of positions, but I really wanted to go further and to specialize. And so I did a PhD with the topic in optoelectronics. And again, underpinning photonics and microwaves together, I looked at the devices for fiber optic communications and specifically looking at semiconductor lasers and the characteristics of them when they were being directly modulated from a microwave perspective. So I completed my PhD in '92, and then I started working at the university. So first, I took up a position at the University of Queensland. That was the department where I did my bachelor and PhD study, and it was an interesting recruitment process that the department undertook because the selection committee comprised a number of the professors in the department who all knew me. So I wasn't sure if that worked in my favor or not, but it was interesting at my interview. One of the things that they asked me, I think they thought that I would be a good recruit for the department. But at the end of the meeting, they asked me what the intentions of my husband were. My husband was also finishing his PhD in the same department. And they immediately thought that if my husband leaves Brisbane, then so would I. And so they were very hesitant to offer me the position because of that. So I assured them that he was going to stay. And so I was offered the position. And what was interesting to see how that situation evolved is that it was actually me who ended up leaving Brisbane 8 months after I was appointed, and not because I was following my husband. So I joined the University of Melbourne in September 1992 as a lecturer in the Department of Electrical Engineering. And I was recruited there by Professor Rodney Tucker, who those of you in photonics know, he's very famous in the field. And he was a former University of Melbourne graduate that had gone around the world and gone on to AT&T Bell Labs and was recruited back into the department to set up a new photonics research laboratory. And during my PhD, I had actually reached out to him during doing some work, reading one of his papers. And so he remembered me and contacted me at the University of Queensland and asked if I would be interested in coming for an interview, which I did. And so I joined the department and I joined the Photonics Research Lab, and that really kickstarted my research career and led to some great opportunities. And Professor Tucker has remained a mentor throughout my life, and I'm really happy to see the celebration of extraordinary men in science and engineering as well, because I have many male mentors who have really supported and helped me make my career a success over the years. So I stayed at the University of Melbourne until 2004. I was appointed a chair of telecommunications in that year, and I was the first woman professor in the School of Engineering. And ultimately, I didn't end up staying long because I ended up going back to the United States, but I'll tell you that part of the story a little bit later. But I have really had great opportunities at the University of Melbourne to establish new research programs. And at that time, what was really evolving in the field of fiber optic communications was to look at fiber optic links for also transporting wireless communication signals, so not just digital baseband signals. And this really appealed to me as a research topic because it combined the two things that I loved, photonics and microwaves, and brought them together. And so the concept of this sending radio signals over optical fiber is really to use optical fiber and all the benefits it has as a transmission medium. So the fact that it has low attenuation and low attenuation as a function of frequency as well, led to a lot of work around the world looking at specifically using fiber to replace more conventional coaxial cable for these types of applications. And so what I've showed here is the different frequencies of the radio standards around the world. And radio signals for different wireless communication signals ranges from 900 megahertz all the way up to 80 gigahertz. And there was really great research work to be done and research problems that needed to be addressed in how to successfully transport these very, very high frequency radio signals over optical fiber. And that is really where my research team did some very interesting work. And that's what we ultimately became very well known around the world for solving those different types of problems. So this concept of photonics and microwaves together and radio over fiber signal transport is an example of that, is more generally called, or one part of the multidisciplinary field of microwave photonics. And it's a really interesting one because it brings together those two different worlds. And as I said, it was initially spurred by interest in using all the advantages of optical fiber as a transmission medium for transporting RF signals. And in fact, it really was the defense world that started doing a lot of interesting work in that area in the 1970s. And it has really evolved over the decades to encompass so many different things now, because photonics can bring all of these different capabilities to different types of microwave systems. So whether it's wireless communications or developing very fast measurement systems, looking at terahertz photonics capabilities, signal processing, and also from the defense perspective of sensing, surveillance, and radar. And I had an opportunity to contribute to a number of books on microwave photonics, specifically on transporting radio signals over optical fiber. And there have been a lot of different focus journals and review articles on the topic as well. And it's something that is a topic that's been very interesting to see over time, how it has really evolved and encompassed so many new different applications as well. So going back to the University of Melbourne and specifically the work that I was doing there, So this is a photograph from the 1990s. It's always interesting to see how my hair color has evolved over the years. But this is a photograph of me with my students at that time, developing some different setups. So we looked at a number of different research problems at the time. We looked at explore different approaches for how to actually transport these high-frequency radio signals over fiber successfully. Different techniques using some novel semiconductor lasers for generating very high-frequency signals well up into the millimeter wave frequency range. Because this is transporting a radio signal over fiber, the radio signal itself has data modulated onto it. So part of this research problem is also not just how do you actually generate this very high frequency signal, but how do you get the data onto that frequency signal initially? And we looked at some very novel ways in which you could do that also from an optical perspective. One of the key problems when you're looking at transporting analog RF signals over optical fiber is there's a lot of impairments due to the characteristics of the optical fiber, specifically with respect to the impact of fiber dispersion, and particularly as you go up higher and higher in frequencies. So we looked at different techniques for overcoming optical link impairments as well. And then we looked also on the microwave hardware side on the setting up a wireless communication link and being able to successfully transmit data in both directions, and also looking at implementing the connection between your optical hardware and your antenna and how you could simplify that as well. So this is just an example to talk about the different types of impairments that you have in these analog radio over fiber links. And, you know, from a research perspective, it offered us great opportunities because there was so much work to do, because you have impairments all the way along the link itself. So starting from when the antenna receives a radio signal and you go from the electrical to the optical domain, the device that you use in order to do that, whether it's a laser or an optical modulator, has certain characteristics associated with it. Some of them are that it has a nonlinear transfer characteristic. It generates intermodulation distortion products. You have noise involved. You have a limited conversion efficiency as well, which limits your overall link gain. And then you have a similar perspective on the other end, going from the optical to the electrical domain, and afterwards you do the processing of the radio signal. And the photodetector itself has some nonlinear characteristics and other aspects associated with it that you need to take into account in order to get the best overall link performance. And as I said, the fiber has characteristics of dispersion, which also impacts the phase noise of the resulting generated RF signal, and also creates RF power penalties. And we did a lot of work on trying to address those specific problems. This is one example of a solution that we developed in order to mitigate the impact of fiber chromatic dispersion. And here we developed a technique using a single optical modulator or a Mach Zehnder modulator. And the technique that we developed was to create optical single sideband modulation. And the way that we were able to do that was to apply the RF signal or the wireless signal itself onto the optical modulator, but onto both RF ports with a 90 degrees phase shift. And what this does is allows you to actually suppress one of the sidebands. So when you have conventional intensity modulation of a semiconductor laser or a optical modulator, the optical spectrum looks like a double sideband spectrum with a carrier. So what you should see here is an optical spectrum where you see the wavelength in the middle, and then you can see two sidebands, or here you can only see one because we've suppressed one. And that type of spectrum is called an optical single sideband with carrier. And why this helps you with respect to dispersion is because by suppressing one of the optical sidebands, when you get mixing of these wavelengths back at your photodiode to recover your microwave signal, you don't get the cancellation effect because of the impact of dispersion on the other optical sideband. And that's how we were able to successfully overcome fiber dispersion. And so when you look at very high frequency signals transported over optical fiber, the link distance that you can transport that signal is really limited to only 1 or 2 kilometers. And we were able to show that by using this type of modulation scheme, this very simple way with a single modulator, we could really get overcome this RF power penalty that you see here in the lower plot, and really get a very nice flat response where you are mitigating the impact of the dispersion and you don't get that impact on your power penalty. And this became a very well-known technique, and a lot of people then started to use this as a way to mitigate dispersion in these types of systems. So another example of some research work that we did, as I said, we also looked at the communication side and actually establishing the wireless communication signal. So not just transporting the radio frequency over optical fiber, but putting data on it. And we wanted to do these types of demonstrations bidirectionally, because that's a real communication system. And here's one example of an experiment that we did. And this particular wireless communication link worked up at 38 gigahertz. As you go higher and higher into the millimeter wave frequency range for your signals, it gives you an opportunity to really put more data on it because your instantaneous data bandwidth is increasing. And this is also the trend that we see now with respect to moving to 5G systems and 5G systems operating in the millimeter wave frequency range, where you have more bandwidth available to put much higher rates of data onto that. And it's been very interesting to me to see how the communication world has really evolved over time. And the work that we did several decades ago, looking at these very high frequency millimeter wave links to get more and more data onto them, are now really becoming an actual reality with 5G networks. So this is an example of an experiment looking at bidirectional links, and we looked at different types of techniques. You can see here we used our optical single sideband with carrier technique to overcome the dispersion. We had a very long length of optical fiber that we demonstrated. And in the upstream direction, we also had some other types of lower cost devices. So one of the issues always with these types of systems is cost. Having these very high frequency components does increase your cost. But you have advantages in being able to get a simplified system. But if you can also do some clever things by doing some frequency down conversion, that you can also exploit lower cost optoelectronic devices as well. So that's a little bit about the work that I was doing as a professor at the University of Melbourne. And my life then took a turn. So I was there for 12 years, and I had the opportunity to now go on sabbatical. So I went to sabbatical, but first to the UCLA, and then I spent some time at the Naval Research Laboratory. And at the time of arriving at NRL in Washington, that was back in 2000, there were a number of people who were also leaving the Naval Research Labs. And the reason they were all leaving was because we had the telecommunications bubble at that time. And there were lots of startup companies being established, and all of these engineers were leaving to have an opportunity to participate in that. So they also said to me and my husband as well, who was doing his sabbatical, oh, you should come and talk to some of these companies. So we thought, well, that's an opportunity to do that. And we interviewed and we were offered positions because they were very keen to get as many engineers as possible. And so now we had this opportunity to join a startup company in the US. But here was the difficult part, because we were also tenured professors at the university, and but we had this great opportunity as well. So what we did is we created, hedged our bets a little bit and created a safety net and negotiated with the university to allow us to take a leave of absence for 2 years in order to have an opportunity to work in industry and get that experience. We both felt very strongly that it was important to get experience outside the university. And the university was also very supportive of that as well. So this led to the second stage of my career. And I like this particular saying from CEO of 3M, Jeffrey Nicholson, which talks about when you're at a university and you're doing research, and research is transforming the money that you get from your sponsors into knowledge. And when you go into industry, it's about transforming that knowledge that has been created into money. And that is really what innovation is. And so, Bashena asked me what really motivated me to go into industry. Part of it was that to really be able to apply all of the knowledge that I had accrued over that time, but also was to be challenged. I also always like to be challenged and to learn new things. And sometimes it can be quite terrifying being thrown in at the deep end. But I always love that challenge, and I always feel that I grow as a person being challenged in that way. And I certainly found it challenging. So the company that we joined was called Dorsal Networks, which eventually was acquired by Corvus. And the company was located in Columbia, Maryland. And it was a venture-backed startup developing ultra-high capacity long-haul telecommunication systems. And at that time, the company was in stealth mode. So when we interviewed there, we actually didn't really know what it was doing. I think we were told something completely different. So we only learned what we were going to be working on once we arrived. So all of this was new to me. I had no understanding of what product development was. So it really was baptism by fire for me. I got an opportunity to be able to use all the knowledge I had about photonics and devices and wavelength division multiplexing. But I really learned so much about what was required to create a real product that could be deployed in the field and customers would buy, and what was really required from all of the technical specifications for something like that. It really was a great experience. It was also very, very challenging. And it was my first opportunity and exposure to leading multidisciplinary teams, because I had engineers working underneath me who had physics backgrounds. Some of them had a chemistry background. They were firmware engineers, mechanical engineers. So it was very, very interesting. And there's a photograph here of the team. This is just a team developing the actual submarine line terminating equipment. And on the right-hand side is the WDM equipment that we ended up developing. And it took us 2 years to develop that. And ultimately, I think it got shrink wrapped and is probably in some warehouse somewhere in Maryland right now. It actually never got deployed. But it was a great feeling to have actually developed this hardware and have it work as well. So, it's interesting to see how this company evolved, because eventually we were acquired by Corvus, and the work on this particular long-haul system stopped. And part of that was because, in a sense, the technology was ahead of its time. Since then, there are a number of companies developing undersea network hardware using the exact same technology that we were working on at that time. So product development is always about being at the right place at the right time. And ultimately, we weren't at that moment, but it was a great learning experience. So what grew out of having that particular exposure to working in industry from a venture-backed perspective was to transition a little bit to something that was a privately held company. And so I had an opportunity to be involved in co-founding a company called Farad, and we're now called Octane Wireless. Farad comes from photonics and radio together, and also it's a pun on the unit of capacitance as well. So we were founded in 2003. We're located in Maryland, and we're a privately held small business. And in a sense, there are two core product areas of the company, and they really reflect the key backgrounds of the two main technical people in the company. So one is antennas, and the other is microwave photonic technologies, which is my background. So the work that we've been doing in our company on the microwave photonic side is really twofold. One is looking at technologies for communications. So this concept of transporting radio signals over optical fiber for commercial communications. And the other part is sort of more defense focused in looking at microwave photonic technologies for RF sensing as well. So on the communication side, this is some work that we were doing in conjunction with the applied physics labs and looking at how to use optical fiber as a transmission medium for transporting very high frequency signals, specifically at 60 gigahertz. And some of you may know that 60 gigahertz is an unlicensed band. It's been available for some time around the world. And because it's unlicensed, it really gives people an opportunity to develop these links and install them very easily. So you have a lot of bandwidth available at this very high frequency, which gives an opportunity, as I said before, to exploit the high bandwidth and the data rates that are available to you. So it really enables this access to multi-gigabit per second data rate wireless connectivity. And the point of that is really to support all of these new bandwidth intensive multimedia applications, the same way that 5G networks now are trying to support those types of applications as well. The other way in which you can use a 60 gigahertz link is to enable a point-to-point link and have a data bridge effectively or a wireless bridge over this type of backhaul network. But where we really wanted to do this work is because you can use optical fiber to efficiently deliver these signals at very high frequency, carrying very high amounts of data as well. And so, as I talked before about the impact of fiber dispersion, and this is also a real problem when you're looking at transporting a 60 gigahertz signal over optical fiber. So we looked at different ways in which we could mitigate this impact of dispersion. We used the concept of that optical single sideband technique as well. But we also looked at another way to mitigate this, which was instead of suppressing the optical sideband, you actually suppress the carrier itself. So what you end up with is at the photodetector, at your wireless access point, you have the two sidebands mixing with one another. And again, because you only have one RF signal being generated, you don't have the other RF tone that can effectively cancel out. And so you can mitigate fiber dispersion in that way. We also looked at some other approaches to actually generating this very high frequency signal. And one approach that was developed by Applied Physics Labs was this concept of a stimulated Brillouin scattering fiber laser, which this shows the setup here. And it's a very clever technique because it allows you to effectively create a suppressed carrier signal with two different wavelengths. And so when they beat together, you get this very high frequency signal being generated. And by adjusting the cavity, you can tune the RF signal over a very wide frequency range. And you also have an opportunity to be able to put data onto that signal as well. And so this spectrum here shows this dual wavelength optical spectrum that this fiber laser creates, which has very, very low phase noise as well, which has another benefit. And you have an opportunity to modulate it as well. So you can see here one of the wavelengths has been modulated. And on the next slide shows an example of a actual link demonstration that we did using this approach. So we had this fiber laser and we separated one of the wavelengths and we put the data directly onto that single wavelength. And then we had a wireless link, and we did this link demonstration actually at APL, and from one building to another, and then we recovered the data and we were able to successfully extract the data on the other end. So this was an example of being able to use different techniques, novel techniques, and successfully send high amounts of data at very high frequencies over optical fiber in a real-world demonstration as well. And we sort of extended that work to look at a bidirectional wireless link as well. And I talked a little bit before about some of the challenges in developing the remote wireless access point, which is from a cost perspective. So one way that we tried to mitigate that was to actually use a lower cost device for transmitting the upstream data. And this is the technique that we developed and that we developed the hardware to demonstrate, so that we had a bidirectional data transmission. And in the upstream direction, we used and designed a special circuit to actually separate the data using an IQ mixer. And so that we were able to use a lower cost commercial off-the-shelf transceiver that you use in data centers, for example. And we were able to demonstrate that successfully. So I talked before about 5G, and it's been really interesting to see now how the 5G standards have been evolving. And so in the company, we're also adapting some of our technology specifically to target the emerging 5G frequency bands. And there are different countries around the world that focus on different frequencies, some in the mid-band region from 1 to 6 gigahertz, and some in the very high frequency millimeter wave frequency region. But I would say more generally, the focus now is on the lower frequency bands. The higher frequency bands started to be demonstrated a few years ago from a point-to-point perspective, but now in terms of really widespread deployment, they really focused on the lower frequencies. And so we've been evolving some of our technology in order to support these types of systems working at those frequencies. So I said that the other part of the microwave technology that we've been developing here in our company is for sensing applications. And sensing and surveillance networks is something that is becoming increasingly pervasive. And photonics can really provide an opportunity to enhance the overall performance of those types of networks. And what I'm showing here is just a very general depiction of what a surveillance network might look like that incorporates fiber and photonic technologies. So at the you may have an antenna array that is doing the sensing of different types of signals, and you have fiber connection to that remote antenna array. So in the direction, in this direction, where the signal is going over optical fiber to that antenna, and it's going to be transmitted. And then in the receive direction, you would have the signals from those antennas being received and going back to where they would be processed. And so you can use fiber in both directions. And the technologies that are really relevant here is looking at how do you do that remoting successfully in order to meet the performance requirements that you need. How do you integrate the optoelectronic components with the RF devices and the antenna itself? And also on the reverse side, going back upstream, how do you connect the antenna to the amplifier? Typically, you'll need a low noise amplifier because the signals that are being received in these sensing networks are very, very low in power. And then how do you integrate that directly in order to make this efficiency of the modulator better as well? So there are a lot of interesting technology issues that need to be addressed in order to develop these successfully. So we've been looking at a number of different aspects of these types of systems for RF sensing. Part of it is looking at the remoting of these very low power signals over optical fiber. And where you have a challenge there is that you really need to be able to transport those signals in a very linear way with very high dynamic range over a wide frequency range and also instantaneous bandwidth as well. On the transmit side, you need to generate RF signals with low phase noise as well. And then there are a lot of interesting technology issues to address on actually integrating the RF photonic front end. As I said, the devices, optoelectronic, microwave, and the antennas together as well. And here's a photograph of some equipment that we have developed for these types of applications. And this equipment's also been recently flight tested as well. We had an opportunity to do that. So there are a lot of different ways that you can improve the linearity of the fiber optic link for these types of sensing applications. And one of the key challenges is to get a very high spurious-free dynamic range over a wide bandwidth, and that's a real problem. And really, it's related to the fact that your conversion process going from your electrical to the optical domain is inherently nonlinear, whether you're directly modulating a laser or whether you're using an external modulator itself. And there have been a lot of different techniques that have been looked at on how you could address this and how to get rid of that type of distortion that you get, these unwanted nonlinearities. You can do it both doing some kind of pre-distortion or post-distortion. You can do different types of linearization as well. And we've looked at a number of different linearization techniques in order to be able to do this successfully. One way that you can do this in a very simple way is if you're using an external modulator, you could bias that modulator at a different point in its transfer characteristic. And this is something that we've been able to do quite successfully. And what I'm showing here is a slide or a result that how you can, by moving away from the typical bias point of your modulator, you can increase your spurious-free dynamic range. And that technique works quite well. And we were able to do this at a very high frequency range, working at 28 to 38 gigahertz for a particular application that we had. And we did a low biasing. We also used a particular type of modulator, gallium arsenide, that is inherently more stable as well. And we were able to get almost record dynamic range characteristics for this link. We've also looked at feed-forward linearization as well, which has a number of benefits. One of them is that you don't need to know beforehand what type of distortion is resulting. You're correcting for it in real time. And this was some hardware that we developed for a Navy program, where we developed a system where we were able to correct for the distortion of that link inherently by being able to, first of all, extract what the actual distortion was, then convert that distortion into the optical domain, and then effectively cancel the distortion optically rather than in the RF domain. And we use various different types of control systems in order to be able to do this in real time as well. And so here are some results showing what kind of suppression of these nonlinear distortions result with this particular hardware. We've also looked at using a different type of linearization, looking at it in the digital world and using digital signal processing to do the linearization as well. And this was some collaborative work that we did with applied physics labs, where we, first of all, did some optical frequency down conversion so that we could then digitize that signal using commercially available analog to digital converters. So by being able to down convert in the optical domain, you have a number of benefits. You get a lower frequency signal. You can convert it down using an ADC, and then you can build your linearization algorithm into the signal processing itself. And we were able to show good results using this type of technique as well, being able to get benefits on relaxing some of the requirements on the optical devices and also on the DSP devices as well. And I'm showing here just a result from this particular setup where we were able to get very good suppression of the unwanted nonlinear distortion terms. So that's a little bit about the technology that we've been developing in the company. And what's also been exciting, both in terms of working on the technology, is also being able to commercialize it as well. And so we've developed a number now. We have a number of off-the-shelf hardware components, looking at very high performance photonic transmitters and receivers at frequencies going all the way up to 50 gigahertz. We've developed an optical distribution system for switching of RF signals in a RF distribution system, and this uses an optical switch in order to do that. So we're doing the switching in the optical domain rather than the RF domain, so your hardware can become much smaller and it's independent of the actual RF frequency itself. And we also have developed some circuitry for actually controlling the different elements in our subsystems as well. For example, a controller for an electro-optic modulator. So I wanted to leave some time for questions, but I wanted to finish up today after talking about technology is to sort of come back to, you know, the focus of this seminar series and the focus on gender diversity in STEM. And I wanted to talk and really have a sort of a call for action for everyone, because it's always important to highlight why diversity is so important. And sometimes I hear questions from people saying, well, why do we want, why do we need to have more women in STEM? And it's not inherently obvious. And what I always like to highlight is the power of diversity. And ultimately, coming from now an industry background, you know, industry recognizes that diversity of thought is really essential for innovation. And we really need to highlight this as much as possible. And so there are all these data points that show that diverse teams are basically lead to increase in the bottom line of the company. And that's why companies and organizations are so focused on increasing the diversity of their teams and their workforce. So diverse teams are more likely to experiment, to be creative, share knowledge, and ultimately that leads to an increase in performance. And I like to show real data that highlights the value of diversity. Companies that have diverse leadership are also more likely to report higher market shares than those that don't. And diverse teams make better decisions. And so it's all types of diversity, you know, gender, age, geographic diversity, race, everything. And the data is all pointing to why diversity is so powerful. And I always want us to remember that. And that is fundamentally why, we always need to think about the value of diversity. So with that, I'd just like to finish by, I would like to want to thank all my mentors over the years and all my collaborators. I'm trying to get to my final slide, but it's not working here. And also the various sponsors for our work over time as well. This is a photograph of me from a few years ago. You may remember that social media thing where it was like, what does a woman engineer look like? And we all took a photograph of ourselves in our workplaces and what we do. And we said, I look like an engineer. So with that, thank you so much for having me today. It's been a real pleasure to talk and give an opportunity to talk about my career and some of the decisions I've made. And I look forward to answering any questions if we have some time. Thank you, Prashana.
Thank you so much for this fascinating talk. I could speak forever. You presented your talk, presents the power, beauty, and excitement of multidisciplinary research, all kinds of things. You show that science is strongest when science works together. You absolutely, on 3 continents, you manage and balance in cultures from 3 continents. And here I speak to you from Santa Monica, California, home of UCLA, where you spent some time. So anyway, way, I open for question because I would, look, she talked about control, this is my domain. She talked about the noise, this is my passion, modeling noise. So I would speak forever on parts of your talk and achievements. But now I open for questions. I already can see, and you probably also see in chat box, you can see the question. Can you, Dalma?
Yes, I can. So I think the first question is from Kristen Lundgren saying that I didn't know that you had developed optical single sideband with carrier modulation, which just goes to show that women are less likely to be acknowledged as inventors in industry than men. How can we help to boost each other's visibility? I mean, that's a great question, and I think that you know, an opportunity like this, like with the seminar series, is a great way to boost visibility. But I think what we need to really be very proactive in always putting our people front and center, and I think that women probably tend to do that better than men may do, because it's very important to always think outside your own immediate network, and always think in terms of not just people that you know directly and putting them forward for particular roles. I think that particular example of not being recognized is something that I see quite often actually in research. When something is first introduced, say, in a particular year, and then it gets referenced for perhaps the next decade, and then after the next decade, people don't go back that far. So I see that happening quite often. But I think the visibility is a key part of what we need to do with our networking and our promotion of each other as well in various roles as well. So in our volunteer roles, but also within our technical communities as well, and always being very proactive and deliberate in putting people forward and making their opportunity or their contributions well known.
Look, the next question is interesting. What should men do better to encourage women in their careers? Many of them do great job. Many of them, as you said, as you demonstrated. But maybe you have also advice what they can do better.
Well, I always say that it's not just a responsibility of women to promote women, but everybody, and that's why I always promote diversity, that this is everybody's job, that they need to promote diversity because it's so important. And then it's the purview of everyone to be proactive in promoting diversity. So for Tom's question, I would just say that just to keep diversity and the promotion of diversity front and center in everything that you do. Because I think that sometimes there's that thought process that this particular problem belongs to just a few of us and just a few champions. But I think we all need to be champions.
Maybe other questions? You also have a two-body problem, and it seems like you solve very beautifully and no problem. You created a professional community in your home.
I think that was perhaps more serendipitous than anything. So I think it's just sometimes when you work in a similar field, you can manage things a little bit more easily, I think, than when someone is in quite different professions.
Any other question? You can unmute yourself and ask a question. If not, Cynthia, I don't know, you probably will, or Jen, you probably will close, but I wanted also to add one observation that Dalma showed the beauty, power, and really excitement of engineering as a field that spans all STEM fields. And this is absolutely beautiful door you open to all other speakers, and we will have incredible picture, huge, broad picture by the end of the year. Janet, Cynthia, maybe
So,
you can.
Cinzia, how much longer do we have? I see 2 more questions in the chat. You are the boss. You tell me.
Right, I would like to see if Dalma has got time, and maybe we can have a few more minutes for the last couple of questions.
Yes, that's fine.
There are a couple of technical questions.
Thank you, Cinzia. Yes, that's why I wanted to address them. So, Dalma, if it is okay, I can read them for you,
Yes.
because the chat is getting crowded. So, Cinzia asked, well, thanks you, of course, and she would like to ask if the technology you presented could be adapted to quantum communication in the microwave regime.
That's a very interesting question. I think there are opportunities because, certainly at the device level as well, and it will be interesting to see how that evolves because, quantum is such a hot topic at the moment. And I'm sure that there has an opportunity to adapt some of those types of concepts specifically to quantum at microwave frequencies as well, and also at the higher frequency in the terahertz range too.
Thank you. There is another one from Ramalata, and is microwave range communication is said to impact the nature, endangering certain species of animals and birds. Can you tell something about it?
Oh, so you're talking about the power of microwave systems, and so basically systems are deployed to be fundamentally to be safe to both humans and wildlife. I think that from a safety perspective, there are things that are deployed along with the actual system in order to make sure that basically you don't get proximity to those particular high power systems, and you have something like that happening. I think safety, when you're specifically talking about very high power, whether that's more for a radar application, for example, there are a lot of safety controls that are looked at. For wireless communication systems, they don't tend to be as high in power, although it's still not necessarily something that you would be wanting to stand right next to it. But again, safety is a key part of how these systems are deployed.
Lovely. And if it is okay, I would like to ask a last question. And this is something I try to ask when I see scientists this powerful. Is there any specific topic, and even outside your field of research, that you think that should have more scientific attention, that could be a potential field for interest or research for any of the scientist attendees that are hearing your presentation today?
Well, so I think that there is a lot of interesting work still to be done on 5G. So I think that there is a lot of not necessarily hype centered around 5G networks, but there is still can be a little bit of a disconnect between 5G from a research perspective and 5G and what can actually be deployed. So I'm interested to see some more research that's sort of focused on looking at some aspects of 5G systems from using more of the technology that is being deployed right now, rather than from the more specialized type of technology that can be done in a laboratory, for example, and to show some of these record numbers. So that is the kind of research that may not be as interesting to somebody because it doesn't necessarily have the same excitement of being able to achieve certain things. But I find it interesting because for me, it's very practical. So you have hardware that is actually being deployed, and it's really about how can you successfully use this hardware that is being deployed and being able to adapt some of its capabilities and expand them in order to achieve even better performance than you can. So I like some of those types of investigations as well. So a little bit coming more from a practical industry perspective.
Dalma, sorry, they ask also about contact with you. If you can help somehow to answer how we can reach out to Dalma if additional questions.
Yes, so I'm sorry, I actually didn't show my my title slide with my my email address. So I'm just going to type it in here.
Thank you. Thank you, Boshena. Thank you, Cinzia. Cinzia, I give the floor to you. I just thought we could address very quickly some of the questions in the chat. Thank you.
Thank you. I think we have reached now a time where we cannot really take more of the precious time of Dalma. I would really like to thank her very, very much for being our first speaker, our inaugural speaker for this series. And it has been really a fantastic talk. And I really hope that this really would be a seed for discussions and maybe cross-fertilizations, as we said, because you have been really putting so much into that, that it will give ideas and really will be a way for more discussions. It triggered definitely in me a lot of questions, and I might really get back to you. So I hope it will happen also for all the others. Thank you very much to Božena for being a fantastic chair of this series. Thank you, Jen, for your words. It was really wonderful. And of course, thank you all of you for attending this very first seminar. And I hope you will also be coming back for all the extraordinary speakers that we are going to have throughout the year. So thank you very much, all. And thank you again, Dalma. It has been really inspirational. It was wonderful, really, to have you. It has been really an honor.
Thank you so much.
Thank you so much. Thank you for the opportunity. And I'm looking forward to hearing the rest of the seminar series and all the other celebrations for the 25th anniversary.
Thank you. It will be fantastic to have you.
Thank you.
Bye-bye,
Bye,
everyone.
everybody. Thank you all.
Thank you, Cinzia.